Hello, my name is Nara Roach, and this is Lab 5, Motions of Falling Objects. So basically what I'm observing in this lab is a basketball and coffee filters dropping. So the basketball is going to be my fast object dropping, and the coffee filters are going to be my slow thing dropping. So my objective in this experiment is to use the momentum principle in the assumption that the net force of a falling object is equal to the sum of the force of gravity and drag force to model the motion of the falling object. So let me go ahead and show you my videos. So here I have my roommate. He's dropping a basketball from a certain height, and so I have basically the axis, and so I have the positive y direction going downward since that's the motion of the ball. It makes it easier when I'm modeling. And so I have the calibration stick set right there, and that is a pro-size basketball. And so the diameter is 29.5 inches, and that's converted to meters. So let me show you how to drop it. As you can see, the location of the ball, and that's clicked at the center of the ball. Let me show you the video for the coffee filters. Alright, so here I have the coffee filters held at a certain height, and so I have the axis set right in the middle. That's actually like in the center of the door, and I have my calibration stick. So I measured the hinge of the door, and that's about 4.5 inches, and that's converted to meters. So let me show you the video. So as you see, as it drops, I have the distance clicked, and that's clicked at the bottom of the coffee filters as it falls. So now that I've finished the video, let me show you my code for the model. So as you hear over on the left, I have my code for dropping the basketball. Here I have my initial conditions. So I have the mass of the basketball, which is 0.624 kilograms, which is the mass of a pro basketball. I have the initial position vector, which is 0, 0, 0, and I have the initial velocity vector, which is 0, 0, 0, because I'm just dropping it. My start time is 0, and I have a time step of 0.01. So that's very small compared to the overall length of my video, which is about half a second. All right, so I have my code, and then so I have the force of the gravitational constant, which is 9.81, and so then I have the force of gravity vector, which is just going to be acting in the positive y direction since I set the ball moving down is my positive direction, and so we know that the force of gravity is the gravitational constant times the mass of the ball. And so I have the overall net force on this is just the force of gravity. So let me show you the video. The model actually. So there it is, and so now let me also show you the one for the coffee filter. So for the coffee filter, the initial conditions are changed a little bit. I have the mass of the coffee filter is 0.0052 kilograms, and the initial ball's position is a negative 0.629. So since I set it above the origin. And so the ball's initial velocity vector is 0, 0, 0 since I'm dropping it as well. And so I have everything for my code is the same as it was for the basketball. And now let me show you the codes for the same two objects, the basketball and the coffee filters, this time with the drag force. So I have the same initial conditions for both. But now in the code though for the model, I now have to make a code section for the drag force. So I have B, which is the constant proportionality, and I have it set for 0.09 for the basketball and negative 0.0068 for the coffee filters. Now I've tested this multiple times, and this is the value that I can get where it is closest to the observation data. And I also have V, which is the magnitude of the ball's velocity. So it's the x component of the velocity squared plus the y component of the velocity squared plus the z component of the velocity squared, and then that's all added together, and then that's I took the square root of that value to get the magnitude of the velocity. So the magnitude of the drag force is this constitutional proportionality times the magnitude of the velocity times the ball's velocity, and the overall net force is the force of gravity, which is in a downward direction, or in this case, the positive y direction, and the drag force, which is upwards, but in my case, it is the upward direction. So I still have the same code for the same model equation for the ball's velocity and the ball's position. So let me show you what this looks like. You see it, so that's that one. Looks very similar to the one before. Let me show you one for the coffee filters. You can see it reaches a constant slope here, so that's a little different than what the other one was for the without the drag force. So now let me show you what all the data in Excel. Alright, so here I have the model for the basketball, and this one on the left here is the one with no drag force, and the one on the right is the drag force. So as you can see from the data, the blue is the observation data, and that's in both, and the red is the model data. As you can see, the observation data, it kind of reaches a constant velocity, it looks like right here. And as you see, it gets pretty close to the model data, but it splits apart. So if this were to be, say, run for 2 seconds, you'd see a huge difference between the observation data and the model data. But as you see, the drag force, even though don't necessarily line up that well, they both reach a constant velocity. And so if we were to run this for 2 seconds as well, the data would be much closer, even though it won't be exactly, but it'd still be very close, almost similar to this. So basically, based on this, it basically means that my model for drag force wasn't that accurate, but it still did a decent job of modeling for the basketball leagues. Now let me show you the coffee filters. So this is for the model for the data for the coffee filters. So as you see, the left one is the one without drag, and the right was with drag. So as you see, there's a huge difference between the model data and the observation data for the coffee filters without drag. It's a huge difference. Even this is only run up to about 0.8 seconds, so this isn't much longer, but a huge difference. So as you see, without drag is obviously not a good model, and it shows the coffee filters definitely had a huge drag force. So here we have the model with the drag force. You can see it's much closer. You can see the initial position and final position are matched up pretty well, but the middle points aren't matched up too well for the drag force. But it actually shows that just means as I said before, that my model for drag isn't that accurate, but it does still do a really good job of modeling the drag force for the coffee filters. Alright, so now for the what does it mean? Well, as you can see by my data here, for without drag and with drag, the with drag clearly shows terminal velocity. As you see, at a certain point, the velocity becomes constant and travels in constant velocity. As for without drag, as you can see, it never really reaches a constant slope. It's still increasing quite a bit. So if this was run for 2 seconds, it'd curve a lot more and more up. So the model with drag clearly shows that it reaches terminal velocity. The only thing I changed in my code for both the basketball and the coffee filters is the initial velocity vector. So I changed that to 1, so that's 1 meter per second. So now instead of being dropped from velocity of 0, it's dropped with the y component of 1. And that is also the same for this one right here. So here I have it thrown with drag. Here's the one for the basketball, here's one for the coffee filters. As you can see, the red one is one where the velocity is just dropped, and the blue is where it is thrown. And so, as you can see, there's a pretty big, significant difference between between when it's thrown and dropped. And you can see the overall velocity would be much greater after it's thrown instead of dropped. And that shows the same for the one with the downward with the drag force. As you can see here, the model with drag still shows that it reaches a constant terminal velocity or constant velocity, and the model for without drag doesn't. As you can see, the model for the drag with coffee filters does show that it reaches a constant velocity. And this one, also for the drag for the basketball, shows it reaches a constant velocity, but much later than it does for the coffee filters. But also, as you can see here, that it reaches a terminal velocity probably a little bit faster than it does when it was just dropped. And the same for the one with the coffee filters. So now let me show you the models without drag. So in the same way I did I changed the code for the ones with drag, I did without drag. All I did was change the y component of the velocity to 1. So as you can see here, that there's a pretty significant difference in velocity and position traveled for both the basketball and the coffee filters. As you can see, both of them still don't reach a terminal velocity. And as you can see, it moves a lot quicker and reaches a much greater final position. So thank you for listening.